And just as a backup, let's start recording locally also. Okay, now we are all set. So we have started recording. We'll start off with the discussions. Now in the previous week, we have been discussing about primarily shear force and bending moment diagrams. Now, if you have thought about it a little bit, you must have realized that in terms of what you have been doing in solving the problems in understanding, that part involving the shear force and the bending moment diagrams, they barely touched anything directly with stresses and strains. Okay, I repeat, they barely touched anything directly with stresses and strains. What you had to actually do for any problem was to basically solve the unknown reaction supports, the internal forces and the internal moments along the beam. And then once you had the expression of them, you just had to plot it out. So directly, there was nothing that you were doing directly with stresses and strains. However, it is extremely important to appreciate that those bending moments and shear forces, they owe their origin. They arise because there is a distribution of stresses over any particular cross section. Okay, so I believe I must have mentioned this earlier, perhaps even while during studying torsion, as well as in the previous week, that the story proceeds somewhat like this. That first of all, you have this three-dimensional body over which there is some kind of mechanical load. And then, as a result of that mechanical load, you have the body undergoing certain kinds of deformations. Now, because there are internal resistances to those deformations, that is why we have the generation of stresses. Depending on the nature of the loading, if it is a torque, you end up with shear stresses. If you have transverse loadings, as we had been discussing in the previous week, you end up with shear forces and bending moments, and those shear forces and bending moment directly have to do with shear stresses again, but different kinds of shear stress, which we'll study in the next chapter. But in this week, we are going to focus our attention on the bending part. It is extremely, extremely important. All over the mechanical sciences, you cannot design an engineering structure without keeping in mind, without taking into account the bending moments. Okay, just like torsion was extremely important, bending is also extremely important. Please also understand that right at the very beginning of this course, we are studying these chapters in isolation, as if when torsion is taking place, there is no transverse loading on the member and there is no bending moment. And when we are studying bending moment, we are thinking of it in a very clean-cut textbook kind of fashion, that there is bending moment and there is no torsion. But in reality, in a real engineering structure where lots of complications are going on at the same time, you must appreciate the fact that those things, not just torsion and bending moment, shear forces, and a host of other things will be taking place simultaneously. You must also very much appreciate the fact that whatever we have been studying till now, it has to do with the statics part of it, as if the body is not moving. But at the same time, you are all studying, both the manufacturing and the mechanical guys, you are all studying, I don't know whether the QM guys are studying it, but at least the mechanical and the manufacturing guys, you are all studying the subject of dynamics. So those kinds of dynamical effects may also come into the picture in the design of things. And why just stop at the dry part of things? You also have the stories associated with the wet part of things. I mean to say the influence of various kinds of fluids in the mechanical system. So right now, at the very beginning of your studies in mechanical engineering, you are studying things in isolation and in super isolation within the various chapters. But as we go forward, you will see that we'll try to bring things together. Okay. All right. With this little bit of funda, and a bird's eye view of what you are studying and why you are studying it, let's actually get down to the business end of things as far as the bending moment is concerned. Okay, so the thing particularly that we will be focusing on, trying to focus on in this week is how the deformation associated with bending looks like, and what is the connection between the stresses and the bending moment. And that is what is actually referred to by that phrase flexure formula. Okay, so the flexure formula is basically a connection between the stresses, the normal stresses that arise at a particular cross section within a beam, and the bending moment which you have been calculating in your previous week. Okay, so the devil is always in the details. So this is the part where we go into those kinds of details. Before we go forward, I'll just take a minute to ask you if you have any question, any lingering doubt in your mind or something. So based on whatever I have been telling you about without writing anything regarding the stresses or anything, if you have any kind of lingering doubt or anything that is not making a direct connection in your head, please tell me. Even if I don't have the time to answer it now, as part of my delivery of the contents, I'll try to keep in mind those things and try to explain those things. If you have any question regarding what I have said till now, what am I talking about, these stresses and bending moments, what is stress, what are the things, just tell me freely. Don't feel shy.
Sir, I had a doubt about the convention, sir.
Yeah, just tell me the question.
Like, what if suppose we have a like a vertical beam, then in that case, how will we do the convention?
Suppose you have a what beam?
A vertical beam. Suppose an electric.
I think you have posted this question, right?
Yes, sir.
Yeah. So I mean, that is just a matter of convention of how you do it, and that's not a fundamental doubt. Okay, so that can be addressed. It's not a problem. Okay, that's not a big problem. Okay. I think you're only worried about the plus and the minus signs there. That's not a problem. Okay, yes. So since your mind is absolutely like a clean slate now, let me try to add something on it. Okay, so bending, deformation and flexure formula. So as I said earlier that we are going to study things in isolation. And when I say bending deformation, what I mean to say is that the beam will be under pure bending. There shall be no axial forces directly on it. There will be certainly no torsion on the beam. So it is pure bending. Okay, so when I say this, I mean pure bending. All right. So what are we actually looking at here? So think of it like this, that let's say we have a beam which is like this, and I am not illustrating to you directly the cross section of the beam. We are just looking at it from the front. So when I say pure bending, I mean something like this. Now you can understand that in reality, you won't have a beam like this, which is just floating around in air. It is like that, no? That the way that I have drawn, it looks like that. The beam is floating around in air. It is certainly not like that. So what is actually happening is that you have a long beam over which there may be certain transverse loads, there may be certain distributed loads, whatever. Now, over a certain section of the beam, then if you draw a bending moment, you will see that bending moment diagram, you will see that, you will see that maybe over a certain part, over this section, maybe the bending moment is constant like this. Okay, so the bending moment diagram is such that over a certain length of the beam, the bending moment is like this. So what we are trying to say is that over that section, the beam will be under pure bending, and not just pure bending, it is under a state of a constant value of the bending moment. Okay, of course, these things can be generalized to non-constant values and then long beams over which different kinds of loading are take place. But right now, for us to develop the theory and to understand the basics, let us consider the simplest of situations. Okay, so this is not really a beam which is floating in air. Rather, this is only a part of the beam which is of concern to us. Okay, so in that sense, you try to understand it. Next question is, as I have told you earlier, our whole focus has to do with this week the connection between the stresses and the bending moment. Okay, so let us try to draw a cross section, keeping in mind that we want to address the simplest possible situation. Okay, so let me draw the cross section and let me tell you after that why I'm taking a cross section like this. So earlier you may have intuitively always think that when you draw a diagram like this, perhaps this is either a circular cross section or a rectangular cross section, but it is certainly not essential for us to have only those two kinds of cross sections. Okay, it can be beyond circular, it can be beyond rectangular. For example, I have drawn a trapezoidal thing here. Okay, it's a nice symmetrical trapezoid. So it is a trapezoid such that there is a nice vertical symmetry about it. Okay, or rather I should say horizontal symmetry about it. So suppose you draw a straight line like this, these two sides are the mirror images of each other. Now that is very important. Okay, for the kind of theory that we are trying to develop here, this kind of horizontal or the left-right symmetry that is of extreme importance. Okay, it is not to say that we do not have theories and understandings of the beams for which that kind of symmetry breaks down. It is not like that. We do know certain things about that, but those are more advanced topics which are covered under the purview of unsymmetrical bending, which you're not going to cover. Okay, in your second year, maybe in courses like advanced mechanics of solids later on. Okay, so we are going to consider these nice symmetric sections, and we are going to, so maybe you can draw this entire beam. Almost looks like a loaf of bread. Okay, so something like that. Something like that. Now, you understand that if this particular cross section has this axis of symmetry, you take any cross section along the length of the beam, it will have the same cross section because it is a prismatic beam. Okay, so let me write that. A prismatic beam is one whose cross section does not vary. Okay, so cross section does not vary along the length. That is what is meant by prismatic beam. So we have this nice prismatic beam. It has nice left-right symmetry, and this kind of a symmetry will be present no matter which cross section you take. You take a cross section here, same kind of left-right symmetry will be there. You will have an axis like this. You will have an axis over here. So overall, you can understand that there is actually a plane of symmetry for this entire beam. Okay, so you have a nice plane of symmetry for this entire beam. So this orange colored thing that I have just drawn, that is the nice plane of symmetry. Okay, now as far as the loading is concerned, so we have talked about the symmetry of the geometry. Now this loading also is symmetric. So you have to understand that this loading is actually on that plane of symmetry. Okay, this loading is also on that plane of symmetry. So that everything is symmetric. The geometry is symmetric, the loading is symmetric. If any one of this symmetry or any one of these two symmetries they break down, either the geometry is no longer symmetrical or the loading is not symmetrical. For example, it can very much happen that you have not only this kind of a bending moment, but rather you have also a bending moment like this in the horizontal plane. So the effective bending moment will be something along this direction. Okay, in that case, we say that even though the cross section is symmetric, but the bending that is going to take place, it is going to be unsymmetrical bending. So again, I'm repeating that we are not concerned with those kinds of advanced topics right now. First, we need to understand the very simplest of cases. Only then we will be mentally prepared to tackle the harder cases. But even in these kinds of so-called simple cases, you will see that there are certain things for which you will have to be really careful. And even in a professional environment, you will see that even with this symmetrical kind of things which are apparently simple, you will be able to design very sophisticated structures, even with this kind of basic theory. All right. So now, with all these stories and all these assumptions and simplifying things that is going on, we are still nowhere, it seems, closer to connecting the stresses with the bending moments. How do we go about doing that? Okay, so you see what I'm trying to arrive at is that on the left hand side or the right hand side, there will be one M. Okay, I should be able to write an M, and that should be written as a function of some stress. I don't yet know what kind of stress components will be there, but I want to write an equation like this, either like this or sigma is equal to some function of M. This is my whole objective. Okay. Now,
sir, excuse me, sir.
Yes.
So we are considering a pure bending moment. So you mentioned that there will be no axial stress.
No, I said there will be no axial loading.
Okay, sir. Okay.
Yeah, that's a different thing. I'll come to that. Very good point. We'll come to that. Okay. So it is like in chess, you arrive at a stalemate where neither player can proceed. It seems like that. Okay, we have this nice picture in front of us. We also know what we want to do, but how do we make this next step? Who can tell me? If you have already read the book, you know some clues, then don't tell. But only if you are picking up right now live in class and you have some ideas, tell me. What could be the possible way out here? I told you.
So do we include the elongation of the object due to some bending or so?
Elongation of the object due to some bending. So you are already started thinking about the bending deformation.
Yes.
Good. Yeah, good. But I'm asking about something more detailed. I told you, right, that M is equal to F of sigma. Okay, that is my objective. So purely in a mathematical fashion, if I ask you that what will be my logical next step in trying to connect the bending moment to the stresses, how will you do that? I'm not asking about the physical basis of this or anything. Like mathematically, in terms of the mathematical expressions, what do you think we should do? I'll give you a hint, okay, to everyone. We have the bending moment here, okay, and we want to connect it to the stresses. For the time being, just forget stress. Okay, if you have just a bending, if you forget bending moment, suppose I ask you that you have a moment and you have to understand how this is arising, how a moment is arising. How so? Go back to the basic definition. Yeah, go back to the basic definition of moment and tell me how a moment arises.
So for a couple of forces acting.
Couple of forces acting, or you take the moment of a force about a certain axis or a certain. Right. That is the basic definition. See, no matter what hi-fi things we may say or lo-fi things we may say, it does not matter. The basic definitions which you have studied, not just in your first year, but also during your JE days, that must hold true. Okay, suddenly those basic things disappear, that cannot be true. All right. So we understand that the moment, this moment that we have been talking about, all these bending moments that we have been drawing in the previous week, they must arise as a result of taking the moment about a force about a certain point or axis. Okay, this is our motivation. So let me go to the next slide and illustrate this in a more specific way. So we draw this cross section again, slightly bigger this time because we want to have a nice clear picture. And let me draw the axis. So what I will do is, perpendicular to this thing, I will draw the x-axis. This is my x-axis. This is my choice, okay? But this is a choice which is like, well, it's not a free will kind of thing. I have basically taken the same kind of coordinate axis as it is given in our textbook. Okay, it is very much possible to have slightly different kinds of choices. Okay, so we have this nice right-handed coordinate system x, y, z, and we are interested in investigating the origin of this kind of a moment, this m. Okay, so this m, you tell me in terms of a vector representation, the way that I have drawn this kind of a curved arrow, this is not a real vector representation. It is just a way of denoting the sense of rotation that is associated with this bending moment. But in terms of the actual vector representation, what is the actual vector that is what is the actual vector associated with this m that is pointing towards? Which direction is it pointing towards?
Towards
K cap.
Towards k hat. Yes, towards k cap or k hat, or the very simply speaking towards the positive z axis. Okay, so so you understand that the vector associated with this is actually like this. Okay, I'm drawing a double arrow because just to denote this n. Okay, we understand that much. Now, as I was telling earlier, we have to connect this to some kind of force. Okay, so here is the little thing that you have to understand. What we do is we take a little element anywhere along this cross section. Okay, this is a very small element of the cross section. We are taking a small element with the motivation that the force that will be exerted on this elemental part of the cross section, that is for all effective purposes not going to vary within this small element. So over this little element, the force is going to be a constant. Okay. Now you tell me what kind of force could possibly give rise to this kind of a moment.
Sir, which are along the x-axis?
The force must be along the x-axis.
Yes, sir.
Any other possibility?
So y-axis also possible.
Along the, if the force is along the y-axis and you want to take the moment about which point? So let me first draw the first suggestion, okay, and then we'll come to the next one. Suppose I do draw the force like this. Let me draw the blue color. Okay. I'll just change the position of this, otherwise it will become a cluttered mess. So this is my force, okay? Let's call this dF. If I take the moment of this infinitesimal force dF about the z-axis, okay, if I take the moment about the z-axis, this is the moment arm. This green colored vertical line that I have drawn, this is the moment arm. And if I take the actual moment, if I curl my fingers in the proper direction, what will be the moment associated with this force? Or which direction will it be?
Minus z.
Very good, minus z. Because you understand, it is r cross f. Okay, so what you have to actually do, you have to translate this. This is the R, okay? So you have to translate it here and then rotate your fingers in this direction. Okay, so that your thumb will be pointing along the minus Z direction. It's much easier to show these things in an actual blackboard, but okay. But I hope all of you will understand. Okay, so R cross F will be in the negative Z direction. All right, let's write this. So M, we have a certain sense, and this thing will be the minus of R cross F. Now, tell me in terms of the X, Y, Z, what is this R really? This
Positive
R,
Y.
yeah, positive Y. So this R is basically just the Y coordinate of this little element. You understand that I have drawn it very big just to make this thing clear to you, but in reality, it will just look like a very small point. Okay, so for all practical purposes, that point will have a certain distance from this Z axis, and that is basically given by the Y coordinate of that point. So we write this Y. This Y is the moment arm. Y times dF. Okay, so dF is the force, Y is the moment arm, this is the moment. And this integration has to be carried out over the entire area, certainly. Okay, so we have struck at the basics of it and come out with some expression. But still it does not involve anything to do with the stress. How can we connect the stress with it?
Hello, sir.
Tau
So
dA.
dF by dA is sigma.
dF is equal to sigma times dA.
Yes, sir.
dF will be
Hello,
equal
sir.
to sigma, yeah, sigma times dA. Which sigma?
So the axial component, axial stress along sigma x.
So sigma x.
Sigma
Yes.
xx.
Yes, say like that. Okay, so now you're in your second year, we are studying mechanics of solids. You have to be very, very specific. Okay, so you have to say properly sigma xx or sigma yy or sigma zz or tau xy, tau yz. So we understand that we are talking about the force which is pointing along this direction. So the direction is along the positive x axis, and we are talking about this kind of an area which is lying on a plane which is perpendicular to this x-axis. Okay, so yeah, so this df, it is actually associated with the sigma xx. So sigma xx is the relevant stress, dA is the elemental area, sigma xx times dA, that is the force, that is the elemental force, multiplied with the moment arm, that gives us the moment. That gives us the moment over the elemental area dA, and this integration over the entire element, over the entire cross section, that will give us the moment which is associated with the distribution of the normal stresses over the entire cross section. I will repeat. We are considering this elemental area dA. On that elemental area, we have this sigma xx. So sigma xx times dA gives us this elemental force. This elemental force, sigma xx dA times the y, the moment arm calculated from the z-axis to that elemental area, that gives us the total moment over that elemental area. And when I integrate over the entire area of the cross section, I get the bending moment which is associated with this sigma xx distribution over the entire cross section here, this entire cross section. This is the story. And now you see that earlier I was desiring to have some kind of a connection between the moment and the stress, and here I have it. I have some other things associated with it, but all in all, I do have M written as a function of the stress, of one of the stress components. Okay, so this is the thing. But the story is not yet complete. Okay, it is far from complete. You see, earlier I had mentioned that we are talking about pure bending, meaning that in terms of the external loading that is exerted on this body, we have this kind of a M. But we do not have any axial force, we do not have any torsion. Okay, so let's consider about the axial force. Axial force is 0. This is what we are saying. Now you tell me, let me write like this, okay? And please understand, so let me not write F because I've already written F here. Let me call that P. So P is the axial force. What is, in general, the expression of P associated with? Meaning to say that which component of the stress is it associated with? Please understand that the direction of this P is the same as the direction of this dF. So it must be sigma xx into dA. Since we are only talking about forces, there is no question of any moment arm or any such complicating things. It's a simple thing. So sigma xx into dA is the dF, and that entire integration of those dFs over the entire cross section, that will give me the whole P. But according to the given situation or the situation that we are considering, this P is equal to 0. Okay, so one equation we have is that this M is equal to this thing. The other equation that we are having is that sigma xx dA is equal to integration of sigma xx dA is equal to 0. These are two of the most important relations. Okay, within the purview of pure bending. Now, it is extremely important to understand one thing. This equation is equal to 0. It is true only under this kind of an integration. What I mean to say is that over individual little elements that you may consider, it is absolutely not necessary. I repeat, it is absolutely not necessary that those individual forces over the little elements, they will be 0. Okay, they may not be 0. In fact, they are not 0. Okay, as we'll see, they are not 0. However, when you integrate those forces over the entire cross section, they turn out to be 0. They must turn out to be 0 because the total external force is 0. Which means what? The immediate implication of this is what? Immediate implication is this, that over certain part of this cross section, the forces will be positive, and over certain other parts of the cross section, the forces will be negative. And they will be distributed in such a nice balanced fashion that the overall summation of that, which is basically represented by this integration, will be 0. Okay, so does anyone have any doubt about these two things? How the moment is arising and how the total force is being written? Think about it for a few seconds. Okay. Since you're all silent, let me proceed. Okay, I'm sure there will be some doubts as we move along and talk about more sophisticated things. Always try to connect back to these two things. Okay. Now we are at such a situation that we have managed to achieve our desire of connecting the loadings with these stresses, but beyond this we cannot say anything. Okay, because we are still talking only about forces and loadings and all those things. Okay, we have included the stresses, but how does it connect with the deformations? Okay. So in order to do that, I mean, this is where the thing gets really complicated, and this is why a lot of time went by before an actual theory of beams was formulated. And believe it or not, it was not formulated by engineers. It was formulated by mathematicians. And even then, even though it was formulated by mathematicians, it was not watertight. Okay, so but the thing is that even though it is not watertight, meaning to say that there are certain flaws in that theory, it is a very successful theory. You see, there is a difference between pure mathematical truth and and a mathematical theory which works. See, any common mathematician can come along and give a theory which is internally consistent and very nice. Everything is nice and correct. But it takes a genius mathematician to show that even though the theory may not be perfectly all right, but it is extremely useful. All right. So with this background, I'll present to you something which is one of the most famous things in all of mechanics of solids and actually all of mechanical engineering. Okay, so the thing that we're going to step into next, it is certainly a beam theory when we are going to talk about the deformations, but there are certain key assumptions, simplifying assumptions, which are stated before this theory is started, before we write this theory. Okay, I mean, the actual connections between the stresses and the deformations, it's not such a complicated thing, but the underlying simplifying assumptions, you really need to think long and hard about it to see why it works, why it may not work, and what are the possible inconsistencies in that. So let me try to illustrate to you. So the theory is referred to as the Euler-Bernoulli beam hypothesis. Okay, please understand that this is a hypothesis, and it has been, it has become a theory because it has been kind of proven within air quotes. Okay, it has been kind of proven through experimental matches, and it works beautifully in many common engineering situations. Okay, so the theory that we are going to study is the Euler-Bernoulli beam theory. Both Euler and Bernoulli were mathematicians. I'm sure you have heard of them. The only confusion is regarding this name Bernoulli because there were a number of Bernoullis. There was an entire family of Bernoullis, uncles and nephews and cousins and whatnot. If I remember correctly, this particular Bernoulli is Daniel Bernoulli. Okay, and Euler is of course Euler. There is only one Euler, the greatest of them all. You have all heard of him, Leonhard Euler. And a lot of mechanical engineering owes its theories to Leonhard Euler. Okay, so not just mechanics of solids, even in fluid mechanics you will see. All right, so what are the basic assumptions behind it? Okay, I will not write them down because so if you want, you can write them down in your notebooks. Okay, the first one is that plane sections remain plane. Okay, or maybe I can just type it out quickly. Okay, so the first one is that plane sections remain plane. This is the first one. I'll tell you what it means. Otherwise, a sentence like this, it makes no sense. Next, plane sections remain perpendicular to the longitudinal axis. All right, and the final one is that plane sections do not change dimensions. Three innocent looking sentences, but they are filled with meaning and significance. Okay, so what are we talking about here? So usually you will see that sorry. Oh my God. Why did I make it yellow color? Okay, so even in your textbooks, you will see that the way this is explained is something by taking a beam like this. So we take a beam like this. We no longer consider this trapezoidal thing because it only complicates matters, but that complication has only to do with the drawing, nothing to do with the fundamental basis of this theory. Okay, so we take a beam like this, and what we do is, just like when you have a loaf of bread, you slice it up, so also you draw some kind of imaginary lines like this. Fine. And as per our earlier notation, this is X. Let's say this is Y. And this is Z. All right. And just as before, our bending moment or our moments, externally applied moments, they're acting like this. Okay. So they're acting in this XY plane. So the XY plane is actually the plane of symmetry. Now, if you look at from the front side, okay, front side means looking directly into the Z axis. Then under this kind of a moment, this beam is going to deform in this fashion. It is going to curve upwards. And this is the part where we first start thinking about the deformation of the beam. Please note that when I'm drawing this thing, I'm drawing it in the sense that Euler and Bernoulli thought about it. Okay, and I have to be a little bit careful here in order to ensure that all these lines, wherever they are meeting each other, they are at right angles. That is absolutely essential. So it's something like this. All these lines, they are perpendicular to each other. Okay. So plane sections remain plane. This is the first one. What it means, okay, what this simplifying assumption it means is that under this kind of pure bending, each of these sections, so if I complete this section, maybe if I complete this section, any one of these sections, you take any one of these sections, even after deformation has taken place, these sections which were initially plane, okay, it's plane, it will remain plane even after deformation. So as you can see here, this is still straight. It is not as if this was initially like this, and after deformation, so after deformation, it becomes like this. Not the best of 3D diagrams. It becomes some like this. The whole thing bends, but well, it rotates, but it doesn't become like this. Okay, it doesn't curve. This doesn't happen. Okay, so this does not happen. This happens. So this is what is going on here. All of them, they just rotate. All right, I'm stupidly moving around my hand over here when the camera is not even on, but I hope I'm able to convey the meaning here. Yes, someone was saying something.
So, means how can we say that the correct one is like that? The plane will be plane. It will not be curved, because the whole means if we see each section, then if it will be totally plane, then how it is like means bending. Because
you're absolutely right. We cannot say anything. That is why these are assumptions. These are simplifying assumptions. So the way it works in any kind of theory building is that you proceed with certain kinds of simplifying assumptions, and then based on that theory, you make certain predictions. And then if those predictions of the beam theory, it matches with what you are actually observing from an experiment of a beam, then you say that your theory is kind of successful. Okay, the simplifying assumptions which you had started out with, they are not so bad. So in any kind, so this is the practice of science. You start out with certain hypotheses or simplifying assumptions, and then you proceed with that, make certain predictions of it, and see, test out through experiments whether they are correct or not. If they hold up, then you say that your theory is not that bad. You can never say that your theory is perfectly correct. And in fact, this Euler-Bernoulli beam theory, there are many modifications to it, many. Okay, so, and believe it or not, even today, even after more than 100 years of these things, more than 150 years probably, people are still coming up with new and more refined theories almost on a yearly basis. Okay, so this is an ongoing practice, but the fact remains that for certain kinds of very common engineering structures where this dimension, where the thickness of the beam and this width of the beam is quite small, okay, is quite small compared to the length of the beam, less than, say, let's say 1 by 20th the size of the length, then this kind of assumptions, it works beautifully well. For thicker kind of beams, you will start to see that this Euler-Bernoulli beam hypothesis or the theory, it starts to break down. It will still give you predictions, but it will start to deviate significantly from the experimental results. Okay, but the good news is that in a lot of the engineering structures, even now, okay, even now they build so very sophisticated structures. The Euler-Bernoulli beam hypothesis, wherever these kinds of restrictions are respected, that the length and the width and the height and the width of the beam are much smaller than the length of the beam, then this is satisfied. Okay, satisfied to a good degree. So you must always understand it like this. We do not know for a particular beam what exactly is happening inside it just by doing mathematics behind it. All right. Next is plane sections remain perpendicular to the longitudinal axis. So again, you see our longitudinal axis is like this. This is our longitudinal axis. Okay. Our x-axis. Or you can try to think of it like the xz plane. So in this particular view, our xz plane will just look like a straight line like this. Okay, I'm drawing it separately in order to not clutter this diagram. Now, what we are saying here is that after the deformation has taken place, the longitudinal axis, it looks like this. This is the longitudinal axis. And the simplifying assumption which Euler and Bernoulli they started out with is that even after deformation has taken place, these angles that you see, they remain 90 degrees. That is what is meant by this second one, that plane sections remain perpendicular to the longitudinal axis. And when I keep on saying this plane sections, I mean the plane sections which is parallel to the YZ plane. Okay, these are the plane sections we are talking about. Okay, the ones parallel to the YZ plane. So these plane sections, they are initially to begin out with, before the deformation has taken place, they are perpendicular to the XZ plane. And even after the deformation has taken place, they remain perpendicular to it. Okay, and the final simplifying assumption, plane sections do not change dimensions. Well, what it means is that initially, if there is a certain height of this and there is a certain width of this, after deformation, okay, so when we are saying deformation, we mean this kind of deformation. But if you still take out a particular plane section like this, you'll see that the height and the width of it does not change. Please note, again, I emphasize that this is a simplifying assumption. And this particular assumption is certainly not correct. It works, it kind of works, but it is not correct. Okay, we know that this is wrong. Okay, so there is an internal inconsistency associated with it, but like stubbornly, like just stubbornly, if we just proceed with it, we'll see that the results that we get from it are certainly not very bad, because the change in dimensions that do actually take place because of not because of what actually happens in reality, the change in dimensions, those are very minuscule change in dimensions, very, very small. Okay, and the smaller your length and height is compared to the height and the width is compared to the length of the beam, the smaller those deviations are from this last assumption. Okay, now with this thing, you tell me something. Okay, so what do you think is the implication of this plane sections do not change dimensions that the statement has with respect to the strains? Because whenever we are talking about deformations, we have to start thinking about strains, the various strain components, because they denote, they capture the deformed state of the body. So what I want to do right now is to think about the implications of these statements as it pertains to the various strain components. So tell me, should there be a non-zero value of epsilon yy? And should there be a non-zero value of epsilon zz? Epsilon yy, epsilon zz. So they denote the strains, the normal strains along the y direction. This epsilon zz, it represents the normal strain along the z direction. If we are saying that plane sections do not change dimensions, the immediate implication is that epsilon yy is equal to 0, epsilon zz is equal to 0. We know for a fact that these two things will in reality break down, but they do not break down so strongly that the theory itself becomes invalid. It's not like that. They do break down, but only to a little extent. Next, tell me what happens to gamma xy. So what is the gamma xy denoting? Geometrically, what is it denoting? Tell me. Which angle?
Shear angle.
Yes, it is the shear angle. So it is the change in the angle from the initial 90 degree of these kinds of things. So let me highlight it here. So you see you have a line like this and you have a line like this. And please understand that you have the x-axis in this direction, you have the y-axis in this direction. The z is coming out of the plane. Okay, so when we are talking about gamma xy, we are talking about two line segments which are initially parallel to the x and the y axis. So these two lines are initially parallel to the x and the y axis. So what are these two lines? These are these lines. You come back to the original undeformed geometry, these are these two lines. If I take this one and this one, originally which was this? It was this line and this line. So initially that angle was 90 degrees. Even after deformation, this angle is 90 degrees. So the change in the angle from those initial 90 degrees, how much is it? It is 0. And because it is 0, this gamma xy, as per our simplifying assumptions, it is equal to 0. Next, you tell me about.
So it is for on center line or for every line?
Yeah, it is for every line. So I mean, if you keep on drawing curves which are concentric to these things, you'll find the same thing, right? There's absolutely no. I mean, you take a line like this here. Okay, you take a curve like this here. It's the same story. Here, these angles are all 90 degrees. And that is true because we have already assumed that these lines, they remain straight. Okay, the plane sections remain plane. So these lines, they will all look straight even after the deformation. That is why they'll continue to be perpendicular to all such other curves which are concentric with these things. Yeah.
So can we say this like this is a circular arc?
Yes, we are going to assume that and proceed. That is actually a key point in our derivation. Okay, of course, we'll do that derivation tomorrow, but these are the building blocks of it. Okay, we have to understand these things minutely. So gamma xy is equal to 0. Tell me about gamma xz. So gamma xz, for that you have to look down into the direction of this y-axis. So what will it look like? It will look like this.
Line along Z.
It is just going to look like a straight beam, where this surface that we are drawing, it is the one which is the top surface of this beam. Okay, this top surface of the beam, that is the one which is parallel to the XZ plane. Okay, so please understand that this is X and this is Z, or maybe this is Z. Okay, and you see that this angle initially was 90 degrees. All these angles were 90 degrees. This continued to remain 90 degrees. So within the purview of our simplifying assumptions, our immediate conclusion is that gamma xz is also 0. Okay, there is no change in the angle between these two line segments, which are initially parallel respectively to the x-axis and the z-axis in the undeformed configuration. Okay, the initial before bending configuration, they were initially at right angles to each other, even after deformation. Okay, so when I'm drawing like this, I'm just taking the top view of this picture. Okay, the top view of this picture. You may think that, okay, because it is the top view of this picture, this thing is projecting out a little bit from here, so there will be a little bit of an extra thing here. That is all right. Okay, but as far as the angles themselves are concerned, with this thing which are parallel to the x and the z axis, they remain perpendicular to each other. So gamma xz is equal to 0. And finally, what about gamma yz? So I'll stop here. Okay, so gamma yz, I will continue from here tomorrow, but I'm just telling you very quickly that gamma yz is also going to be equal to 0. It is going to be equal to 0 because you see this gamma yz, it pertains to this kind of a cross section, this cross section. And that cross section, initially it was, this angle was 90 degree. After it has deformed, it has become like this. As I've already told you, it has become like this. But this angle, it continues to be 90 degrees. All these angles, they continue to be 90 degrees. Okay, so this is the y-axis, this is the z-axis. Initially they are right angles, they remain right angle. Okay, so gamma yz is also equal to 0. We have not talked about epsilon xx. For that we'll discuss tomorrow, and that is not going to be equal to 0. Thank you very much. Please go to your next class.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank
Thank you, sir.
you, sir.
Thank you, everyone. Please go to your next class.